The moon is a barren, dead rock, or at least that is what we were all told. Yet NASA scientists are currently documenting flashes of light on the lunar surface that release the energy of a full ton of TNT. We are taught the moon is static, a silent guardian in the dark. But in reality, it is being pelted by high-velocity debris with enough force to shatter bedrock. Why are these impacts suddenly hitting with such intensity? And what happens when the debris field shifts toward the planet we call home? The answers are hidden in the data, but they are not what you expect. For decades, we viewed the lunar surface as a historical record of the early solar system, a museum of ancient craters. But Dr. Bill Cook and his team at the Meteoroid Environment Office have fundamentally changed that narrative. They found that the moon is not a museum, it is a target. We are currently transiting through a region of space where the density of meteoroid streams is reaching a critical threshold. This isn't just about a few falling stars. We are talking about objects traveling at 72 kilometers per second. To understand why this matters, we first have to look at the math behind the impact. And trust me, the numbers are far more aggressive than the textbooks suggested. The inciting incident occurred in 2013. The Mare Imbrium, a massive volcanic plain on the moon, was struck by a 40-kilogram meteoroid. This was not a small pebble. It was a massive object that hit with such velocity that it produced a flash visible from Earth with the naked eye. This event shattered the assumption that lunar impacts were rare, isolated accidents. NASA's Lunar Impact Monitoring Program, or LIMP, has since confirmed over 400 of these events. But the real story isn't the number of impacts, it is the velocity. When an object hits at 72 kilometers per second, it doesn't just crater the surface, it vaporizes the impactor instantly. This creates a plasma flash, a burst of energy that defies the dead rock theory entirely. And what they discovered in the aftermath of these flashes is even more disturbing. To understand the mechanism, we must look at the lunar barycenter. This is the point around which the Earth and Moon orbit, and it is the focal point for incoming meteoroid streams. Think of the Moon as a magnet for space debris. It lacks an atmosphere to burn up incoming objects, meaning every single gram of mass hits the surface with its full kinetic potential. The physics here is unforgiving. Energy equals 1/2 mass times velocity squared. Because the velocity is so high, 72 kilometers per second, even a tiny 1 kilogram rock carries the kinetic energy of a full ton of TNT. This is the brutal kinetic equation that space agencies have to calculate for every single impact. When the Earth-Moon system passes through a dense debris trail, the frequency of these impacts spikes. It is a predictable mechanical process. We are now heading into a period where the orbital intersection is optimal for high-energy collisions. The Lunar Reconnaissance Orbiter, or LRO, has mapped 99% of the surface at 0.5-meter resolution. What it shows is a surface that is constantly, violently, and aggressively being reshaped. This is not a static environment. It is a dynamic, high-stakes battlefield of physics. The escalation comes from our newfound ability to track these events. Before, we were blind. Now, the LRO gives us a high-definition map of the destruction. We are seeing thousands of new, small craters appearing in real time. This is the turning point for our understanding of the solar system. We used to think the heavy bombardment period of the moon ended billions of years ago. The data shows us that the bombardment never stopped. It just shifted. The MEO is now monitoring these streams with unprecedented precision, but the sheer volume of incoming material is challenging our current surface modeling. If the moon is being hit this hard, it raises a terrifying question. How long can our satellite remain a stable shield? And more importantly, as we look at the trajectory of these debris streams, we have to ask what happens if the Earth crosses the path of a stream that is too dense to ignore. The science is clear. The moon is not a dead rock. It is a sentinel, absorbing the blows that, one day, might be directed toward the only home we have. The next week is critical. Scientists are watching the lunar barycenter with bated breath, waiting to see if the current stream holds its course, or if the density increases as predicted. We aren't just observing the moon anymore. We are watching a cosmic game of survival. To understand why the moon is not a dead rock, we must look at the physics of the impact itself. When a meteoroid strikes the lunar surface, it does not merely leave a dent. It triggers a thermal event of staggering proportions. Thermodynamic modeling confirms that at the precise point of impact, temperatures can spike beyond 5,000 Kelvin instantaneously. That is nearly the temperature of the surface of the sun. In that single fraction of a second flash, solid rock vaporizes. It transitions directly from a solid to a plasma state. This is not just a cratering event, it is a chemical transformation of the lunar surface. We see this in the secondary effects known as the ejecta blanket. When the primary impact occurs, it blasts millions of tons of pulverized regolith across the lunar plains, scattering debris across hundreds of kilometers. This process is the primary driver of the transient lunar exosphere. Data retrieved from the LED mission, the Lunar Atmosphere and Dust Environment Explorer, prove that the thin shroud of gas surrounding the moon is constantly replenished by these impacts. It is a breathing, shifting environment fueled by the chaos of the debris stream. Furthermore, the seismic data we possess from the Apollo 17 lunar surface gravimeter provides the hard proof. These instruments recorded distinct seismic signals consistent with high-velocity meteoroid strikes. These were not tectonic shifts. They were the rhythmic, violent impacts of cosmic debris hitting the lunar crust. We are seeing a continuous cycle of destruction and redeposition. Every crater is a record of a recent collision, and the sheer density of these features indicates that the moon is actively being reshaped even as we watch. The energy involved in these impacts is concentrated, intense, and remarkably frequent. We are witnessing the physical erosion of a celestial body occurring at a rate that defies our previous, outdated models of lunar stasis. The science is undeniable. The moon is a dynamic, active participant in the solar system, absorbing the kinetic energy that would otherwise be directed toward our own orbital infrastructure. We are looking at a system that is constantly in flux, a sentinel that is literally being worn down by the sheer volume of incoming material. This is the reality of the lunar environment, and it is far more volatile than we ever dared to document. This volatility presents a massive systemic problem for the next generation of space exploration. We are moving from an era of observation to an era of permanent habitation, but our current engineering is not ready for the reality of this debris environment. Consider the SpaceX Starship HLS. It is a marvel of modern engineering, yet it must account for extreme micrometeoroid and orbital debris shielding. Every square meter of that hull is a potential failure point. If a high-velocity particle strikes a critical system, the cost is not just measured in metal, it is measured in billions. Estimates suggest a single catastrophic impact on a lunar base could result in a loss of $2.5 billion in hardware and mission time. That is a conservative figure. The real cost is the total loss of the mission objectives and the safety of any crew involved. We are currently operating without a global lunar impact early warning system. We have sophisticated sensors for Earth-bound asteroids, but the moon is essentially flying blind. Robotic assets, landers, and future habitats are currently vulnerable to high-velocity debris that we simply cannot track with our current ground-based radar arrays. This leads us to the terrifying specter of the Kessler syndrome. While we primarily discuss this in the context of Earth orbit, the implications for high-density lunar orbital traffic are severe. If we begin to cluster assets in the lunar vicinity, a single collision could trigger a cascade of secondary debris, effectively creating a zone of denial around the moon. We are reaching a point where our ambition is outstripping our safety protocols. The lack of infrastructure to mitigate these impacts is a glaring weakness in our roadmap for deep space expansion. We are sending hardware into a region of space that is effectively a cosmic shooting gallery, and we are doing so with limited shielding and zero real-time warning. If the density of these streams continues to increase as the current data suggests, our current assets will be obsolete before they even touch the surface. The window for intervention is closing, and the stability of our future lunar presence depends entirely on our ability to recognize this threat before it becomes a reality. As we analyze the trajectory of the latest debris stream, we realize that the danger is not just theoretical. It is calculated, imminent, and rapidly approaching our doorstep. How do we survive this kinetic gauntlet? The answer is not found in a single breakthrough, but in an evolution of defensive engineering. We return to the fundamental physics of impact energy. For decades, the Whipple shield has been the gold standard for orbital survival. By utilizing a sacrificial outer layer to shatter incoming projectiles, we convert high-velocity kinetic energy into a dispersed cloud of vaporized material. It is elegant in its simplicity. But the lunar environment demands more. We are moving beyond simple shielding into the realm of active, AI-driven defense. NASA's Artemis program is currently pioneering predictive modeling that does not just react to debris, It anticipates it. By integrating real-time telemetry from the Deep Space Network, these systems calculate the probability of impact in milliseconds. They adjust orbital trajectories before the threat even crosses the horizon. It is a dance of precision at orbital speeds. Yet, even this is insufficient for long-term habitation. We must look to the ground beneath our feet. The European Space Agency is researching regolith-based shielding. Imagine 3D printing structures directly from lunar soil. By sintering lunar regolith into thick, hardened shells, we create a natural barrier against micrometeorite bombardment. This is the ultimate form of in situ resource utilization. We are no longer just visitors, bringing our own protection. We are becoming part of the lunar surface itself, beyond the physical shell. The next frontier is detection. Current radar systems struggle with objects smaller than 10 centimeters. That is why laser-based debris tracking is the next critical unlock. These systems, currently in prototype phases, use high-frequency pulses to map the lunar orbital environment with unprecedented clarity. We are talking about tracking objects as small as 1 centimeter. When you can see the threat, you can avoid the impact. This is not science fiction. It is the cold, hard engineering of survival. We are building the architecture of a permanent lunar presence. Every layer of shielding, every line of code, every laser pulse is a calculated effort to defy the statistics of a high-density debris field. The survival of our hardware, and eventually our crews, hinges on this layered approach. We are building a fortress in the sky, one that must withstand the unrelenting pressure of space itself. We are finally learning that to stay, we must adapt to the environment, not just endure it. This is the shift in strategy that defines the coming decade of lunar operations. The physics of protection is only half the battle. The other half is found in the halls of international policy. Because the moon is no longer a wilderness, it is a strategic asset. The Artemis Accords have laid the groundwork for this new era of cooperation. They represent a framework for shared safety and, more importantly, shared accountability. But the stakes are rising. The United Nations Office for Outer Space Affairs, or UNUSA, is currently locked in intense debate over the long-term sustainability of these activities. They are grappling with a reality that few want to admit. The moon is becoming a crowded, high-value district. Consider the Deep Space Network. It is the nervous system of our interplanetary ambition. If a major debris event triggers a cascading failure, the resulting cloud could sever our communication relays. The economic fallout would be immediate. We are talking about the security of assets valued at over $10 trillion. This is not just about scientific exploration anymore. It is a matter of national security for every spacefaring nation on this planet. The race for lunar resources, helium-3, rare earth metals, water ice, has turned debris mitigation into a geopolitical necessity. If one nation fails to secure its orbital path, the debris does not care about borders. It hits everyone. This is the paradox of our lunar ambitions. We are incentivized to move fast, to capture market share, yet forced to move together to avoid mutual destruction. The UNUSA guidelines are the first attempt to codify this shared responsibility. They are pushing for transparency in orbital mapping and collective action in debris removal. But the pressure is mounting. As private entities join the fray, the regulatory environment is struggling to keep pace. We are witnessing the birth of a new legal frontier, where the definition of sovereignty is being rewritten in the vacuum of space. The stability of our future lunar economy depends on our ability to enforce these safety protocols without stifling innovation. We are balancing on a knife's edge, where a single collision could turn a multi-trillion-dollar investment into a field of useless shrapnel. This is the systemic risk that keeps mission controllers awake at night. It is a global problem that requires a global consensus, and the window to reach that consensus is shrinking. We are now forced to confront the reality that our next steps will determine the fate of humanity's expansion into the stars, as the consequences of our failure are already written in the debris of our past. As we look toward the horizon of 2124, the narrative of lunar exploration shifts fundamentally from the era of visiting to the era of defending. We are currently laying the groundwork for permanent human presence, but the physics of the lunar environment remain unforgiving. The Lunar Gateway, currently in its developmental and early deployment phase, serves as the critical prototype for long-term survival. However, by the next century, the scale of our ambition will necessitate a transition toward automated, AI-managed impact defense grids. These systems are not merely a luxury, they are a prerequisite for human survival on a surface that lacks an atmosphere to burn away incoming cosmic debris. The reality is that long-term climate modeling of the moon indicates that surface stability is the single most important factor for large-scale industrialization. Without the ability to mitigate the constant threat of high-velocity micrometeoroids and larger cosmic impacts, the capital-intensive infrastructure required for lunar mining and manufacturing would be untenable. We are moving toward a future where the moon is treated as a strategic asset, protected by active shielding technologies that monitor the surrounding cislunar space in real time. This shift represents a maturation of our capabilities. We are moving past the experimental phase of the Artemis program and into a period where the moon becomes an extension of our industrial base. The challenge for the next century lies in the integration of these defense grids with the civilian infrastructure required to sustain human life. As we optimize our orbital logistics, the focus will increasingly turn to the automated orchestration of debris tracking and kinetic intervention. This is the necessary evolution of our spacefaring civilization. We are building a reality where the safety of our lunar habitats is guaranteed not by chance, but by the precision of our engineering and the consistency of our global regulatory frameworks. The transition from exploration to industrialization is a path defined by these defensive requirements, ensuring that the investments made today will remain secure for the generations that follow. The mystery of the 9,811 velocity per hour threshold that we opened with is no longer a matter of speculation. It is a calculated reality of modern orbital mechanics, a reflection of the extreme speeds at which objects in the lunar environment interact and the systemic risks that define our current trajectory. We have traced the history of our lunar ambitions from the early days of the space race to the complex multinational and private sector landscape we occupy today. We have seen how the fragility of our lunar infrastructure is directly tied to our ability to manage the debris that we ourselves have created. The future of humanity's expansion into the stars is not just about the technology of propulsion or the science of life support. It is about the governance of the vacuum. The stability of our future lunar economy relies on the consensus we build today. If we fail to establish clear, enforceable safety protocols, we risk turning our most promising frontier into an unusable graveyard of shrapnel. But if we succeed, the moon will become the foundation of our next great economic leap. The next week will see critical milestones in lunar trajectory, mapping, and orbital safety, confirming that the risks we have discussed are not distant, but immediate. We are at the threshold of a new era, and the decisions made in the boardrooms of today will dictate the safety of the lunar frontier for the next century. If you found this breakdown of the lunar economy and the physics of space safety insightful, please subscribe to the channel. We will continue to track the real-time developments of the lunar industrial complex, providing the deep dive analysis you need to stay ahead of the curve. Join us as we continue to document the most important developments in modern space exploration. Thank you for watching.